want you to open up to the page that looks like this in your packet. And if you have an electronic copy, you can follow along with it. And you can use one of these diagrams, and you'll only need one for this class period to follow along with me and then learn how all of this works. And then you can use the rest of these to work problems on the next page in your packet. Right? And so find this spot in the packet and follow along with me, and it'll be very helpful for you. You'll have a really good model for what you're going to be doing in your classwork and homework after this. All right, so what we're talking about is electron configurations, and giving credit where credit is due. I got this PowerPoint slide, although I've edited it. I got this PowerPoint slide from a textbook manufacturer, so I don't want to steal credit for it. So let's quickly review what we've talked about last week and yesterday. The Bohr model had 7 energy levels in it. When Schrodinger went to update this and create the newer model, he kept those 7 principal energy levels, but he realized that they had to be divided into sublevels to accurately reflect the actual energy of the electrons. Right? He discovered 4 different kinds of sublevels, right? S, P, D, and F, which we'll talk about in just a minute. And then within those sublevels are orbitals. So we have, from the largest scale, we have a full energy level. Within that full energy level, we can break it down into sublevels, which is smaller and more detailed. And then within a sublevel, we can break it down into orbitals, which is the smallest and most detailed part of this model. So there's 3 layers to it, and we're going to work our way through it. Once we know what all the orbitals are, then we can build the model back up to create an accurate representation of any element's electron arrangement. And that's what we're going to be doing here today. So I mentioned there are 4 kinds of sublevels. We introduced this yesterday. An S sublevel has 1 orbital, and each orbital can hold 2 electrons. So that's the pattern that you're going to see here. The P sublevel contains 3 orbitals, right, which is a maximum of 6 electrons. Now, just because it has 3 orbitals, an orbital is just a space where electrons could be. And so it doesn't mean that we're necessarily going to fill all of those spaces with electrons. I'll show you what I mean by that as we go forward. The D sublevel is bigger. It has 5 orbitals. And so that means a maximum of 10 electrons. And an F sublevel is the largest that we deal with. It has 7 orbitals and then a maximum of 14 electrons in it. Notice the number of orbitals goes up by odd numbers, 1, 3, 5, 7. So that's one thing that you can use. And then if you know that the orbitals contain 2 electrons, then that's 2, 6, 10, and 14 electrons there. In theory, there could be more sublevels within the atom because there's a lot of empty space, more empty space than there are actually electrons that could fill that space. And so no atom uses any other sublevels that we're aware of to actually hold electrons. So we don't worry about the theoretical other sublevels that could exist. And then finally, yesterday, we broke down the energy levels. All right. Now, the principal quantum number is the energy level number. Right. So that's a key to a lot of information on here. Level 1, right? That means that we're dealing with an element that's in row 1 on the periodic table because the energy level corresponds to a row on the periodic table. And it also means that we have 1 sublevel. So this principal quantum number tells me what row the element is in, and it also tells me how many sublevels are in that energy level. Right? So level 1 has 1 sublevel. Right? The sublevels always start with S because they're the smallest and lowest in energy. So we call that level 1 sublevel S, or simply 1S. It's just a description of which space we're talking about. If I put an electron in it, right, then I'm going to put an extra marking in there, and I'll show you for just a minute, in just a minute, how that works. So there's 1 orbital in there, and the number of orbitals in any energy level is given by n squared. Right? So 1 squared is 1, so there's 1 orbital. And then the number of electrons would be 2 times that, or 2n squared. So there's a mathematical pattern here. And you don't have to think about this algebraically because the pattern is laid out for you in such a way that you can always figure it out visually. And so a lot of people prefer that. But if you like to know mathematical patterns, you'll see that that's carried through all of this. So level 2 means an element in row 2, and it also means there are 2 sublevels in the energy level. So that'd be 2s and 2p, right? Again, that's level 2 sublevel S and level 2 sublevel P. So it's just a listing of the information about that space where electrons can be. right? So 2 squared is 4 orbitals, right? Or we can also think that S is 1 orbital and P is 3. So that adds up to 4, and that makes a total of 8, which is exactly what Bohr said about the second energy level. He just didn't know about all the other detail that's in there. Energy level 3, so there's 3 sublevels, and this would be for an element in row 3 or period 3 on the periodic table. Right, so there's 3s, 3p, and 3d sublevels. Right, that's 1, that's 1, 3, and 5, which totals up to 9. Right, 9 is also 3 squared. And then 2 times 9 gives us 18 electrons, which is exactly what Bohr said without the sublevel information. And then finally, in level 4, so that's an element in row 4 on the periodic table, and that also means 4 sublevels. And those are called 4s, 4p, 4d, and 4f. Notice that it's not enough to just tell what kind of sublevel, because we also have to include the energy level. The 4s is higher in energy than the 3s, which is higher in energy than the 2s, and then the 1s is the lowest in energy of all of them. And so we have to distinguish them because each of these is a space with a different energy for the electrons. So if we add all these up, 1, 3, 5, 7, we get 16 orbitals, and then 16 times 2 is 32 electrons, or 4 squared is 16, and then 2 times that is 32. Beyond energy level 4, we continue the same pattern, so we don't add anything new after that. So level 5 would look just like level 4, except it would be 5s, 5p, 5d, and 5f. Now there's another way, as I mentioned, that you can learn this visually, but we'll have to get to that as we work through this process, and then you'll see hopefully how it all comes together by the end of the day. So that's a quick review, and I know I blasted through that really fast because I want to take the time to do what's coming next. Do you have any questions about anything that I need to clarify what we talked about yesterday? Any specific questions? Now, if you're still just a little confused, or perhaps even a lot confused, and you just don't know how this is all going to come together, that's okay, because for a lot of students, it doesn't come together until you see me work through it, which is what we're getting ready to do. All right, so this is a visual way that we're going to lay out all of these sublevels and orbitals that we talked about. We're going to represent a single orbital as a box, right? So an orbital is a space where 2 electrons can go. So we're going to draw a box, and then up to 2 electrons can be put in that. So it's kind of like putting the dots on the rings for the Bohr model, except we're going to be putting the electrons in a box instead of on a circle. Right, so in the first energy level, there's only one box because there's only one orbital. The S sublevel only has one orbital. And so that's level 1, sublevel S, or 1s. Okay. Then we go up in energy, and we have energy level 2. Right, so level 2 has an S sublevel and a P sublevel. And you can see the orbitals or boxes, 1 orbital for S, and then 3 orbitals for P. These are just spaces that we can fill electrons into, and that's exactly what we're going to do. Just like we built a Bohr model and then added electrons to it, we're going to arrange these orbitals and then add electrons to them. We'll add the correct number of electrons for whichever element we're looking at. And then this is energy level 3. So there's the S, the P, and the D. Notice the big jump here, and that is correct in nature. There is a big change in energy from the 3P sublevel to the 3D sublevel here. Right, 1 orbital, 3 orbitals, 5 orbitals. So this is the pattern that we've been talking about. As long as you have one of these diagrams in front of you and you have them in your packet, then you can always sort of retain this information or figure out anything that you need to do. We'll come to level 4 later, so that's all we're going to work with so far. Okay, so this is the diagram, the fundamental diagram that we're going to use for the quantum model. Just like we used the pre-printed circles that you had for your Bohr models, this is the pre-printed diagram for the quantum model of the atom. And now you just need to learn how to use it, which isn't really very hard once you get the hang of it. Right, so the lowest orbital has the lowest energy, and then moving up, we get higher and higher energy. So anytime a sublevel is higher than another sublevel, like 3p is higher than 3s, it means that that sublevel has more energy. The electrons in that sublevel are moving faster. All right, so let's start with the very first element, like Bohr did, but with our new model. Hydrogen has 1 electron in it. Okay, so where does it go in this diagram that we had? Well, as I said earlier, electrons always want to go to the lowest possible energy space, or the lowest energy orbital that's available to them. right? So we always start from lowest energy and work to highest energy. This principle is called the off-ball principle. And you don't need to know this by name, but it is one of 3 rules that you can remember that govern how we're going to fill in these diagrams. And if you remember these 3 rules, then you can go through any number of electrons for any element and you can get this right. The off-ball principle, off-ball literally means in German to build. So it's just the governing principle for how we build these diagrams. We go from the lowest energy upwards. So we build from the bottom up, in other words. Okay, so we put the electron in the lowest empty box that's available to it. Okay? And that means on our diagram, so again, there's level 1, level 2, and level 3. I'm going to repeat that a lot because I want that visual to stick in your brain here. All right, so I'm going to fill the electron into the lowest box there, right? We're going to represent the electron a different way in this model, though. We're not going to use a dot. We're going to use an arrow. And you'll see why in just a minute. So I'll explain that on the next slide. Okay, so the arrow goes in the first box, the lowest box, and that's it for the hydrogen atom. That's the whole arrangement right there. Now, eventually, we want to get to a place where we don't have to draw all this out and fill in all the electrons. And I'll show you that in just a minute as well. There's a shortcut to this that we can do that saves us a little bit of time. And so once you learn the pattern, you won't even need this whole diagram. You'll be able to just write straight out a very simple code that explains everything we need to know. All right, so moving on to helium, we're building larger and larger electron configurations. That's what we're doing here. We're just going to keep adding electrons. Each time we add an electron, it represents the electron arrangement for a new atom as we go through there. So helium has 2 electrons. We need to add 1 more. Where am I going to put the next electron? Right, well, the rule is we always want to go to the lowest energy orbital, and an orbital can hold 2 electrons before it's full. So it's going to go in the same box that we had before. Okay, but there's something that we have to remember when we do this, and this is a new piece of information that we haven't talked about yet. I briefly mentioned some of this yesterday, though. Every electron in an atom's electron arrangement is actually unique. We can describe every electron uniquely. There's enough information in the energy that we receive from the electrons to distinguish each and every individual electron. And so we're essentially writing an address for every electron within the atom when we do this. So what distinguishes the 2 electrons that go in the same orbital? Well, I mentioned yesterday that electrons spin. This is something that was discovered later, well after Bohr had created his model. Electrons don't just fly around, they spin, right? And when 2 electrons are in the same orbital, they have to spin in opposite directions, right? And again, this is not theoretical. This is something we can actually observe from the light that they produce. So this is something that we know is true. In fact, we're not 100% sure what governs this, and we don't know why this is necessarily, or we haven't fully explained why this is, but we know it happens. And so we're going to reflect this in our model. And so if they have to spin in opposite directions, can you see why I represented the electron with an arrow now? Right, so when electrons are in the same orbital, they have to spin in opposite directions. What we believe is that this helps to relieve the repulsion force between them. Electrons that are in the same space or in a close space to each other would want to repel each other and push away. But by spinning in opposite directions, this allows some of that force to be dissipated so that they can be in the same space. All right, so let's build our model. Again, first 3 energy levels, right? And I've got 1 electron already in there for hydrogen. And so then the second electron goes in with the opposite spin. Now, up and down is a little bit arbitrary. I mean, it could just as well be right and left. When we talk about something as small as electrons, directions don't really matter all that much. So that's arbitrary. I like up and down. You can do right and left, but we need to have arrows because we need to indicate opposite spin. And we can tell the difference between these now. The light that comes out is subtly different between the 2 in a way that we can measure. And so we can tell the spin of the electrons. So we know this is true. What's even weirder is that if I have 2 electrons in an orbital spinning in opposite directions, and then I remove one of the electrons from that orbital, which we can do, we're going to talk about later on in this unit. So I take one of these 2 electrons away and move it somewhere else. If I change the spin of that electron that I took out of the atom, then the one that's still in the atom will immediately change to be the opposite again, no matter how far apart those two electrons are. It's something called quantum entanglement, and it's really weird. It's an example of how strange electrons can be. But it has a lot of promise for long distance communication. If we can find a way to build machines that operate on this, we could change electrons in one place and then they would immediately change their partner electrons in other places, no matter what the distance is. And so it's a really interesting and intriguing technology possible in the future. All right, so helium has 2 electrons. Now at this point, rather than having the whole diagram, there is a shorter way to represent this, and I'm going to tag these along with our diagrams. So think of this diagram not as the end result, but think of it as a teaching tool. It is a map that you can use to figure out how to get where you're going. But eventually, just like when you're driving, you learn the way to another place without needing a map anymore. So with enough repetitions of this diagram, you won't need it anymore, and you can go straight to just writing what we actually call the electron configuration. The electron configuration is simply a list of where all the electrons are in one of these diagrams. So right now, all the electrons are in the 1s sublevel, energy level 1, sublevel S. And then there's 2 electrons in there. And so we can simply write 1s with 2 electrons. Right? Now notice that 2 there, it looks for all the world like it's an exponent. And I want to break you of that impression right away. This is not an exponent. This is not a mathematical formula. This is just a list. So this is just telling me where electrons are. It's in level 1, sublevel S, and there's 2 electrons there. The reason why I raise this up is to distinguish it from the other number that's in here so that we don't get the 2 numbers confused. Right, so it's not 1s squared. We're not going to be putting in a number for S and calculating something. It's not math. It's just a list. Level 1, sublevel S with 2 electrons in it. You'll see how we continue that going forward. This is what I actually want at the end, and the diagram is just a map to get me there. All right, so moving forward, we're going to add a few more electrons. Lithium has 3. And then beryllium has 4. So I'm not going to do every single element, and hopefully on your worksheet, if you're following along with me in the packet, you can do all of this in one of the diagrams. You don't need to do separate diagrams for these. We're just going to keep adding electrons to the same diagram and keep building it up. And then you can just make little notes in the margins. So I'm going to skip over lithium and go straight to beryllium just to save a little bit of time. All right, so again, level 1, level 2, level 3. Beryllium has 4 electrons. We know where the first 2 electrons are. We've already drawn them in the diagram. So then where does the next one go? We go to the next lowest orbital, which would be the 2s sublevel right here. So we just move up the energy diagram. If the lowest orbital is full, we go to the next lowest. When that one's full, we go to the next lowest, and we continue our way up from lower energy to higher energies. So electron 3 goes there, and then electron 4 would also pair up, but with the opposite spin. Notice again, I arbitrarily choose up for the first one. You can do down, up, it wouldn't matter, as long as they're opposites. And then I'll list these places. So I have level 1 sublevel S with 2 electrons in it, and then level 2 sublevel S with 2 electrons in it. Right? So again, this is simply the sublevel and then the number of electrons that are in it. Sublevel and the number of electrons that are in it. We read this as 1s2, 2s2. And again, the number is raised not to make it an exponent, but just to distinguish it. Can you see what I mean here? The 2 2s that are back to back there. We don't want to confuse those 2 numbers. And so we separate them by putting that number up so it looks different. It's a superscript, not an exponent. All right, moving up one more element. Boron has 5 electrons. All right, so next will be the p sublevel, and there's 3 orbitals. All right, so there's 3 boxes in there. They're all of equal energy, so it doesn't matter which box I put the next electron in. And the answer is no, it doesn't matter. They're all equal to each other. Right? The term for that in chemistry is degenerate. Degenerate orbitals have the same energy. I don't really use that word much, but just in case you come across it in your future studies. right? So now that we're in energy level 2, we filled 1s and we filled the 2s. And so the 5th electron goes up here. Typically, I go left to right, but it really doesn't matter. You can fill them in any order that you want. And I just suggest that you be consistent. Follow a consistent pattern, and then it'll be repeatable. And as you repeat it and rehearse it, then you'll learn that pattern, and you will no longer need the diagram eventually. That's the goal. So I'd write that as 1s2, 2s2, 2p1, right? So level, sublevel, number of electrons, level, sublevel, number of electrons, level, sublevel, number of electrons. All we're doing is listing each sublevel that has electrons in it, and then the number of electrons that are there. Notice that these superscripts, 2 plus 2 plus 1, add up to 5, the total number of electrons, which is a way we can double check if we got things correctly. We're putting in 5 electrons because that's how many are in a neutral boron atom. And we know that because boron's atomic number is 5. Okay, so then that brings up, oh, sorry, I wanted to point out to you, because this will come up in a later activity. Notice that there's 1 unpaired electron here. Now that doesn't have any meaning yet, but that's laying the foundation for something later on. So it's just something I want to draw your attention to. There's an unpaired electron there, but in the full sublevels, they're all paired up. All right, so going 1 more electron, carbon. That brings us to our last question. Right, where is the 6th electron going to go? Because we actually have a choice here, right? We have empty orbitals in that same sublevel that we can put the electron into. And we also have the orbital that already has 1 electron. So the question is, do we pair up the electron right away, or do we put each electron in empty boxes first before we pair up? Well, electrons repel each other, and so they would prefer to be separated from each other rather than paired up if they have the option. And so the answer is that electrons would prefer to be unpaired. They'll stay unpaired as long as possible. So that means we put electrons in empty boxes first, a single electron in each box, and then we go back and double up only when each box already has an electron in it. Interestingly, they have the same spin when they're in separate boxes. And again, we know that's true, but we're not 100% sure why that is. Okay, so picking up from where we were, we had 5 electrons in here. So the 6th one has to go into an empty box, and it has to have the same spin. Oh, where'd the arrow go? There we go. I got my animations out of order. Sorry about that. I'll need to go back and fix that. All right, so that's 1s2, 2s2, and then 2p2. Now notice when you look at this form right here, which is called the electron configuration, right? It doesn't clearly show you that these two are separated. And so you either need to know that, or you need to be able to use a diagram to figure it out, because there is a difference between 2 unpaired electrons and 1 pair of electrons that affects the behavior of the atom. And that's something that we're going to look into more later on in the unit. But just drawing your attention to it right now, there are 2 unpaired electrons here. That is not clearly indicated when we do this shorter version, the configuration. This diagram, by the way, is called an off-ball or an orbital filling diagram. And then this is the electron configuration, which is what we actually want. All right, so skipping ahead several elements here. And I'll go through these, but I'm going to end up with neon. So we're going to go all the way to 10 electrons here. All right, so neon has 10 electrons. We've already got 6 electrons in our diagram here. All right, so where does the 7th go? Well, Hund's rule says the empty box. And again, you don't need to know these rules by name. You just need to know how they apply to filling this diagram. And if you follow those rules, then you'll get the right answer every time. All right, so the 7th electron goes in the empty box. And now all 3 boxes have a single electron in them. So now we have no choice but to pair them up. And so there's the 8th electron. That would be oxygen's configuration. There's the 9th electron. Notice opposite spin in each of those cases. That would be the configuration for fluorine. And then finally, the 10th electron, which is neon's configuration. How do we write the configuration in the shorter form? It's 1s with 2 electrons, 2s with 2 electrons, and 2p with 6 electrons, right? And that's how we do electron configurations. And that will continue to be the pattern, with one noteworthy exception. And there's one thing that's unexpected a little bit later on. And other than that, if you can learn that one twist, so to speak, then you'll be able to master this pattern with a little bit of repetition. Also notice that there's no unpaired electrons and that all of these sublevels are full, right? Full, full, full here, right? That's going to be important later on. All right, let me stop briefly for questions. Is there anybody that has any question right now that you would like me to answer? Anything that I can clarify for you before we move on? Anything? Okay, so we're going to continue, still using the same diagram in your packet, so continuing to follow these. Here's a quick summary of the rules we've talked about. We build from the lowest energy up, right? So we build from the ground up. That's what off-ball means. So we always go to the lowest box on the diagram, which is why this diagram is done vertically, to try to help you remember that. We can only have 2 electrons in any box, and when that's true, they have to spin in opposite directions. And then finally, if I have an empty box, the electron would prefer to go in the empty box rather than pairing up with another electron. So in sublevels that have more than one orbital, we put 1 electron in each orbital before we go back and put the second electron. All right, so let's go ahead, add some more electrons to here. We're going to start skipping some elements along the way, and I want to get into the 4th energy level because that's when the twist occurs. Right, so through the 3rd energy level, through the 3rd row on the periodic table, everything works great. Okay, then there's one slight change. All right, so already we have our 10 electrons, and so then for magnesium, we move up to the next sublevel. So we start energy level 3. Now, I want to once again make the connection to the periodic table here. Right, notice that each time I start filling an S sublevel, it corresponds to starting a new row on the periodic table, right? So when we're talking about lithium and beryllium filling this box, right? Well, lithium and beryllium are in row 2 on the periodic table, right? So I started with hydrogen, helium in row 1, then lithium and beryllium, which is in row 2. As soon as I start the 2s, it means I am moving to row 2 on the periodic table. And then once I start the 3s sublevel, it means I've moved to row 3. And magnesium is in the 3rd row or the 3rd period on the periodic table. So again, these energy levels correspond to rows on the periodic table, which can help you to shape your plan so you know where you're going with these when you're filling it out. Since I know magnesium's in the 3rd energy level, that means I know I'm going to be filling in at least the 3s sublevel. All right, so I'd write that as 1s2, 2s2, 2p6, and then 3s2. And again, there's 0 unpaired electrons there, and I'll bring that importance up next week. All right, skipping ahead to chlorine. So we're going all the way to 17. 5, 6, 7, remember in separate boxes, 8, 9, 10, right? Then 11 and 12. Right? The 13th can go in any box. I just choose the leftmost box because that's the pattern we usually use. All right? Then number 12 goes in a separate box, and number 13. So train yourself. Sorry, that wasn't 12. That was 13, 14, and 15. I lost my count there for a second. All right, train yourself to always fill the P sublevel, 1 in each box first, right? And that's a total of 15 electrons. And then we go back and double up. So the 16th electron would pair up and the 17th electron would pair up. And then we're done because that's how many electrons chlorine has, right? So we stop filling in electrons at the atomic number for that element. Chlorine's atomic number is 17. What would the electron configuration be? So 1s2, 2s2, 2p6, 3s2, and then 3p5, right? And that adds up to 17. Again, 2 and 2 is 4, plus 6 makes 10, 12, and then 5 makes 17. So the superscripts, the raised numbers there, should add up to the atomic number for the atom. In this atom, there's one unpaired electron. It's right here. Okay, and that's going to be a factor later on in the unit. All right, so now let's say we fill the 3p sublevel. So I put the 18th electron in here. This would be the electron configuration of argon, by the way. So argon has 18 electrons right there. All right, so if we go beyond the 3p, then something unusual happens, something that surprised even Schrodinger and the other scientists that were working on this. All right, we know that there's a 3d sublevel, and we would expect that that would be filled next, but it isn't. Right? We actually start the 4th energy level first, and then go back and fill this last sublevel in the 3rd energy level. And that's weird. It's called energy level overlap. The lowest orbital in the 4th energy level overlaps with the highest orbital in the 3rd energy level. And this actually gets worse as we go higher and higher. Luckily, there's a visual way to remember this. The periodic table is designed that way. So what did I just tell you? Every time we start a new row on the periodic table, it means we're starting a new energy level. We're filling a new S sublevel. So the clue here is after argon, we don't continue in the 3rd row. Argon is the end of the 3rd row on the periodic table. The next element, which is potassium, is in row 4. And if an element is in row 4, there has to be something in the 4th energy level. That's the rule that we've determined. So that tells me that we're actually going to slide that 4s sublevel in here next. That's going to go next. So after 3p, the pattern breaks just a little bit, or rather, I should say, there's a different pattern than what you would expect. And so you have to learn the pattern that actually is followed in nature rather than what you would like it to be. We would like to go 3s, 3p, 3d. It's nice and organized that way, but it doesn't work that way. 3s, then 3p is followed by 4s, and only then do we go on to the 3d sublevel. So let's fill in 6 more electrons here, right? We're at 18 at this point. So electron number 19 goes in the 4s sublevel, and then electron number 20. That fills up, right? Once that's filled, now can we go back and do the 3D sublevel, right? And so that leaves me with 1, 2, 3, 4 electrons right there. Notice again, in a D sublevel, just as in P, we put each electron in an empty box first before we would ever go back and double up any of the electrons. Okay? So after 3P comes 4S, and then after 4S, we go back and finish the 3D sublevel. This is exactly what we were doing in the Bohr model. Remember, 2, 8, 8, and then 2. That's exactly what we did when we were drawing the Bohr model. It was tweaking the Bohr model to reflect the actual order in which the electrons are filled. We start the 4th energy level before we finish the 3rd energy level. And that's also going to be true in level 5. We'll start level 5 before we finish level 4. Okay? And that continues as we go forward. All right, so let's try one on your own. Try to finish using the same diagram if you have it in front of you. Try to fill in the electrons going all the way up to 35. So that would be 11 more electrons. All right, so we have the diagram right now for 24 electrons. So going from there, try to fill in 11 more electrons and see if you can come up with the electron configuration for bromine, element number 35. All right, so with 11 more electrons, okay, we would fill in, let's see, we were at 24. So number 25 is right here, and then 26, 27, 28, 29, 30, 31, 32, 33, 34, 35 electrons. Okay, so after 3D, we go back to the next, which would be 4P. So you can think of it as the D sublevel interrupts the S and P. And there's another way to think of it, which I'll show you right here. So let's roll this electron configuration in here. There are repeating patterns here, and each pattern repeats 2 times, or it happens once and then repeats once, if you want to think about it that way. All right, so the first pattern is S2. And so I have S2 and then S2. It happens twice. All right, then the next pattern is P6, S2. So P6, S2, P6S2. Okay. Then after the twice for P6S2, we start a new pattern, D10 and then P and then S would be the order there. So that's another way that you can think about it as you go through that. I'll continue to emphasize that as we move forward. That would be the electron configuration for bromine. And again, if I add all these raised numbers, the superscripts, I'm going to get 35 electrons because that's bromine's atomic number.